Okay, let's start. Full screen. Hide the video panel. It works. Seems so. Okay, so I'll just remind you, we started talking about functions, and Sammy just asked me why does calculus is all about limits, and I think we're about to answer that in the next few lessons, because we started studying about functions. We do start with limit of functions, but it's going to be rather quick. And then we'll use the idea of limits in order to define and raise some results and prove them about functions. And we'll see, like we said, I think I even wrote it, continuity and differentiability. I don't know if I wrote it. And on calculus 2, you will see integrability and areas, not in this class. But we will use a lot of the ideas of limit, and you will see them popping every now and again, or always. Okay, so a quick recap: we've defined limits using Cauchy definition. We said that the limit is L if for every area around L in the y-axis there is an area, a punctured area around x0 in the x-axis, such that the y value of this axis is close to L in that very sense. And I wrote it in discrete mathematics logics notation. And I don't even remember why. I think one of you asked it, so I'll blame you. But one of my points here is that when you write it in logics notation, you see why is that definition so complex. Because it's for all epsilon, there exists a delta such that for all x, if the x's are around x0, then the f of the x's are around L. So three quantifiers, interchanging quantifiers, it's a complicated definition. And you can do all the arithmetics of limits like we did with sequences with that definition. We shall not do that, because we're going to give a second equivalent definition using sequences. So it encapsulates, it's like how do you say libraries? It's like, yeah, it is libraries in programming, right? Someone did most of the work and you just use the library. So it's the very same thing here. When we'll define limit using sequences, all of the epsilon of the complexity will be inside the definition of the limit, and all the theorems we've already proved, and we can use that. Sometimes it's better to use the definition by Cauchy, and most of the time I think we'll work with the definition by Heine. And you need to understand that both, mainly because in calculus 2, you will get the definition for integrability, which again uses epsilon and areas and whatnot, so you need it, and for some of the theorems as well. But again, we're studying two equivalent definitions, and when we can, we use the easy one, and you'll see why it is easy. So Heine's definition of limits, that's what we're starting with. And before we start introduction, like I like, introduction, let me tell you a small, I'm not sure if it's another An allegory, no, it's not an analogy, it's an allegory. And in Hebrew, we say mashal. So I'm not sure if there is a word, it's from the really Jewish mashal, I think. And so I'll just write a story, okay? And, but it's not an allegory, mashal.
The direct translation would be a parable.
No, I don't
No?
agree. Mashal, it's like a story with wisdom behind it.
Yeah, that's what I learned in the.
Okay, whatever, maybe. Maybe, whatever. We don't get. And by the way, it's not Jewish. The story itself, I think it's Indian, but whatever. A few, I don't know, whatever. A man comes into the house of the few blind brothers and asks them for shelter in India. I think it matters that it's in India, you'll see why. He comes with something, I'll leave it as that. I never told it in English, so it's not the best storytelling, but you'll forgive me. And the brothers try to understand what it is. So one brother feels and says, this is stone, huge boulder. And another brother says he feels a tent, another a rope, thick rope, another that rock, and a pole, a big pole. I think that's enough. And what is it? What did the man bring to the blind brother's house? Each one of the brothers try touching it and says something else. Do you know maybe the answer? Some people know the answer. They know the story of it. Can anyone guess? The what? What did you say? No. What?
It matters that it's
It matters that in India. I think if it wasn't in India, you would have never guessed the answer. An elephant. And the point of the story is, I got it from a psychology book, but I really like it for Matthew. We'll see in a second why. But like the meaning behind the story is everyone has their own point of view, everyone thinks they're right, but it's hard to see the whole big picture, right? Because one of them touched his foot, and the other one touched his ears, and another one touched the tail, and another one touched the foot, right? So everyone felt something different, but they're all looking at the same thing, right? So that's the moral of the story, psychologically wise. What does it have to do with our subject? Let's look at the following example. suppose we have a function f of x, which I won't tell you, it's like something. And we wish to know its limit. Okay. We wish to know its limit when x goes to 0, say from the right. So one of us chooses an a sequence that tends to 0 but never reaches it, and plug it in the function. So why does that make sense? What is the idea of limit? We say that if x is close to 0 from the right, we are interested in the y values. We plug in values which are close. Oh, I forgot that I said from the right. We plug in values close to 0 from the right into the function, and we look at the y values. And suppose that I tell you that they are all zeros. What can you say about the function? What do you think you can say about the function, about the limit? What does it look like? Yes, Simon.
So
Doesn't have a positive. It looks like 0.
Right to left, the tends to.
Yeah, it looks like it tends to 0. Let's put it in GeoGebra. So let's have 1, 0, half, 0, and third. Let me think for a second. That reaches third, 0, quarter, 0, so forth. So looking at that, these are all supposed to be points on the function. I didn't write the function yet. And it looks like the function, its y values goes to 0. Right? But then another one of us, you are the blind brothers, chooses another sequence which also tends to 0 from the right, but he sees that f of bn is actually 1. What does that tell you? Whether does that make sense? Just fix it up for a bit. That's start from the beginning. We learn. Okay, just a second. So I think that's fine. And 1/1.5. 1, I hope I'm not mistaken. We'll make sure later 1 plus quarter 1. 1, 6. And 1. No, I am Just a second. Well, that's enough for the visualization. After I'll plot the function, I will make sure that the points are the correct places. And what do you think it says about the function? This first person goes over these points and he always sees the y value being 0. The second person go over these points and he always sees the value being 1. What does it tells us about the limit of the function?
It's not as easy as just looking at some points and guessing.
No, but what will be the answer? So the answer is that there is no limit for the function. In this case, there is the limit does not exist. Because in order for it to be a limit, we want that every which way we go towards it, it will be the same y value. It's indeed a limit. So let me just show you the function. Then you will see how all this is possible. The function is actually sine of 1 over not 1, 2 pi over x. So I got almost all of them. I was mistaken with g. So what should it be? Let me think for a second.
Or
Maybe it's 2/3.
or a 2/3.
Not at all.
What is G going to do?
Be here, right? I'm saying this was jumps on the 1. So 2, I'll write it. Drawing black. So 2 over pi over x must equal 2 pi plus half of pi. That's what I need. So 2 over x must equal 2 plus half. So 1 over x equals, and that's 2 pi k. That's 2 pi k. I think I was rather close.
It's fine.
2k plus half. Oh, now I see the half is there and I needed to add here. It's 1 over 2k plus half. So it's 2 plus half. That's where g. 2 plus half. Yay. Wow. Why? Why are you here? Oh, it's 2 plus a quarter. Sorry, I divided by 2. Yay. Okay, and the next one will be 1 over 4 plus a quarter. Yes, that's nice. And why did I skip 1? I don't care anymore. But it's enough. It's enough.
What is 3 plus
And
now 3 plus 4 per minute.
when it comes, oh, 1. Wait, it's last one, 1 over 6 plus a quarter, comma 1. Great. Okay. So again, now I do have the blind brothers, 2 blind brothers. One of them says, I see the limit is 0, the y value is being 0. The other blind brother says, I'm seeing the limit as being 1. And that means that they're both mistaken and there is no limit, because if there was a y value, they should all see the same 1. And again, this is the function, and you see, I hope, why there is no limit. It's like a continuous version of 1 minus 1 to the power of n, because the function goes from 1 to minus 1 to 1 to minus 1, and all in the right area of 0. It also happens on the left. I don't care about that. I can define the entire function to the right.
zero?
Okay, f of x equals if x larger than 0 sine of 2 pi over x. Okay, so we don't care about the left hand side, all of the example is on the right hand side. What is the limit of x? The idea of limit is when x goes closer to x0, in this case 0, we ask what should be the y values. Can you tell me what are the y values at this area? It could be anything from 1 to -1. You have no idea what the y values are, right? It's not definitely, it's even in this drawing, it actually looks like a huge smear, right? Because the wave is becoming condensed.
Yeah, and I was just saying because it's some number over zero, so what is it defined or is it?
No, it's not defined, that's my whole point, right? Because it's sine, if you're looking at the very formula of the function, it's sine of 2 pi over x. When x goes to 0, 2 pi x, 2 pi over x goes to infinity, which makes the sine do infinite cycles. That's why it goes infinitely many times from -1 to 1, and you have no limit because the y values spread. Just like the sequence -1 to the power of n. So now I will put everything we just, this is an actual example, but I didn't give you the definition yet. So after the example, I will give you the exact accurate definition and we will see what happens, but I'm trying to get you to see the idea behind that definition. Yes, Sam? This is just calculation, I'll delete it, I don't care about it that much. Was for the GeoGebra plotting. Yes,
Why would we be using the sequence? What's the need to put a sequence inside a function? Like,
so first of all, that's the subject we are learning, right? Heinz definition of limits using sequences.
but like when you say f of an, is that
It's
Is that-
a lot of when I'm saying f of an, it's not. I see the confusion. It's not that I'm putting a sequence instead of x, but I'm plugging in every each by each. Every element of the sequence I plug into the function, and then I get a sequence of y values, right? An is a sequence of x values. F of an, I'll write it up because that's important. Note an and bn are sequences of x values. When we plug them in, we get sequences of y values. Okay, it's not f of the sequence, it's f of every different element. And the idea is that an and bn are so-called close to x0. And what do we expect f of an and f of bn to be close to? If there was a limit, L, right? We expect that if an is closer to x0, then f of an will be close to L. So what's the definition of close? That's the nice thing. We have an actual definition of a limit. If an goes to x0, we expect f of an to go to L. Okay, that's the idea. And now we'll write it up formally. So now for the formal definition. Eine definition for a limit of a function using sequence. We say that the limit as x goes to x0 of f of x is equal to L. If for every blind brother, if for every sequence an that goes to x0, but again the punctured idea, I'm not like in the function sine of 2 pi over x, I'm not expected to plug in. I didn't write the function itself. We should f of x equals sine of 2 pi over x. I'm not expected to actually plug in x equals 0. And again, Sammy, that's the answer to why is everything about limits. Because what you wish to do is plug in 0. Tell me what is the y value when x is 0? But that's impossible, it's undefined. So what do you do instead of plugging in the actual number 0? What do we plug in into x instead? Numbers close to 0. But that's limits, right? I put a sequence of numbers that tends to 0. Use the definition of a limit. Okay? That's exactly what solves the problem, and that's asymptotes. The same. What's an asymptote? I cannot actually plug in the number I wish, so I look at what happens towards that, the limit. Okay. So again, I plug in numbers that tends to x0, but not actually equal to x0. And what do we expect to happen?
Therefore,
Yes. And the y values about these x values is L. And now a moment of logic. The definition basically says for all an that goes to x0 gets different than x0. It is true that f of an goes to L. So how many quantifiers do you have here? One, exactly. So it's much simpler, but the whole thing is that the entire complexity is with these errors here. When I'm saying that an goes to x0, that's the epsilon definition of limit of sequence. When I'm saying that f(an) goes to L, that's the epsilon definition of a limit of a sequence, right? But if we say we understand limits, we have theorems about that, we just get one quantifier. All blind brothers must report this, that they are seeing the very same thing. Every sequence, every way we go to x0, we wish the y values to go to the same thing. If it's true, it's the limit. And if for two sequences we get different limits here, then by definition, the limit does not exist, because it's not true that it all goes to the same place. That's what we've seen above. Therefore, and just another short note, and I'm not sure that everyone meant. Short notes. And for the right limit, we take a sequence to the right of x0. And if you want the left-handed limit, you take a sequence to the left with a small change in order to accommodate left, right, or two-sided limits. So an example, I will write and formally the definition from above. Sorry, not definition, the example from above. And we are asked about the limit as x goes to 0 from the right of sine of 2 pi over x. I'm claiming that we've proved, almost proved, but I've shown you that the limit does not exist. Now we'll prove it formally. Take an to be 1 over n. Where these are x values, where do they tend? What is their limit?
0.
0. Do they ever reach 0? No. So that is a sequence of positive x values, because it's from the right, positive x values to the right of 0 that tends to 0. So we expect that if we plug in numbers close to 0 into the function, we will find out its so-called limit. Now plug it in the function, and we get sine of 2 pi over an. What is that actually equal to?
The 2 pi n.
2 pi n, exactly. And what is sine of 2 pi n? No, 0.
0.
0. Okay, so again, we took a sequence of x values. All right, we took a sequence of x values that tends to 0 from the right, and we saw that the y values are what are the y values over 1 over n?
0.
0. So that's we're at this point. We're taking these points, and we see the y values always being 0. So we think this function is the constant function 0. That's what we see from this point of view. But it's not enough to look at one point of view for that reason, for exactly that reason. Now choose Bn, which is 1 over
3n.
or 2n plus a quarter. So it's not as easy to see why did I choose that sequence, and as you've seen before, it wasn't easy for me to do it in my head, but you will see in a bit why is that a good choice. Okay, where does it go to? Where does it tend?
0.
To 0, right? Plug it in. We get sine of 2 pi over Bn, which is sine of 2 pi times and 2n plus a quarter. Oh, I didn't need the 2n here. N is enough. Just a quarter. Okay, so that was my mistake there. And then we get sine of 2 pi n plus what? Plus half of pi, which is sine of half of pi. And what is sine of half of pi? 1. That one, so it will be in the same row. So we get 1. Okay? That's why I skipped by mistake these points here because I took 4. If I'll fix it for 3 plus a quarter, that's where I don't skip it. Oops. I already have that on 4. So what is the conclusion about the limit in that example?
Doesn't exist.
Yeah. Therefore, the limit when x goes to 0 from the right of sine of 2 pi over x does not exist. Any questions up until now? So we have the definition and we have our first example. Let's look at the second example. Quite similar, but even easier to be honest. What do you think about the limit as x goes to infinity of sine of x? It doesn't exist either. How can we prove it? We need to take x values here that tends to what in this case?
To infinity.
To infinity, right? Because we're asking about the limit of infinity. What happens when we put very large x? So we'll take an to be 2 pi of n. Where does this tend to? No, the x values themselves tend to infinity, right? 2 pi n. But when you plug that in, sine of an, that is 0. So someone might say, okay, it looks like the limit is 0. I took x's that goes to infinity and the y values went to 0. But we can take a second sequence, Vn, that is 2 pi n plus half. Where does this go? Again, infinity. But sine of Vn is 1. Again, the limit does not exist. Any questions so far? Okay, so we have the definition of a limit by sequences. As you've seen, it's quite easy. I will phrase and prove one theorem about it, show you just how easy it is, and I will not do it anymore. Almost all theorem of arithmetics and of limits follow directly from sequences using that definition. And I will give you one example. And theorem if the limit as x goes to x0 f of x is 1, then the limit as x goes to x0 of f of x to the power of g of x is equal to e to the power of the limit as x goes to x0 of gx times f of x minus 1. So I just, it's funny that Tomas went out, but I just took the rule that Tomas has never seen. And I said, let's write it in a function form. And I'm saying that it follows immediately from the very same law about sequences. Why? Proof. And given an arbitrary sequence AF that goes to x0 gets different than x0, then what can you say about f of an?
What's the f of the x?
No. First of all, x0 not xn, there is no xn. Look at the assumption. We have that limit here. Yes, it goes to 1, because we said that if you plug in into f values close to x0, then the y values are close to 1, right? So f of n goes to 1. Therefore, what can we say about f of an in the power of g of an that goes to e to the power of the limit of g of an times f of an minus 1,
They have to be the same sequence.
which
G of and f of an.
no. The theorem is if this is any sequence that goes to 1, and this is any other sequence, then the power limit is e to the limit of the power times the base minus 1, right? And that's the proof, right? And that's the proof. And the whole idea here is that we don't need to do it again. We have these results from sequences, and then we basically say that because we can define a limit of functions using sequences, we get the same theorem always for free. Okay.
G of an has to go to infinity or something.
No, not even. We just say the base has to go to 1. Actually, just a short note, we ignored the cases where f of an is actually 1, but it is easy to see they work as well. The theorem we studied was if the base goes to 1 but is never 1. But here f of an tends to 1, it may equal 1. But what is 1 in any power? 1. And if you plug in f of an actually equals 1, you get here 0. E to the 0 is also 1. So it also works when f(an) is actually 1. But it's not my main point. My main point is that we can prove all of the theorems, and this in the same manner, it will be a complete waste of time. I would just say take an arbitrary sequence, it works for the sequence, and we are done. Because if it works for any sequence, then it works for the function by the definition of a limit by Heine. And any questions so far? So again, I'm stressing that point. We didn't waste the first 2/3 of the semester. Everything we learned about limits follows immediately for functions, and you can use it. Sandwich theorem, bounded times sequence or function that goes to zero, and all of the ways we learn how to calculate limits are still true. Now we can ask them about functions. We'll also have L'Hopital rule in the future, but everything we learned so far is true, and we just use it without proving it. Thanks to Jaime. And just for general knowledge, some courses in Israel even, but in the world, start calculus by functions and not sequences. So they don't have Heine's definition, they only have Cauchy. And everything we proved with the theorems about the arithmetics of limits of sequences, they do directly on functions using the Cauchy definition. We start with the sequences and we have an easier time with functions. And that way, that's why I like it better as well. We can focus on the calculus properties of function and not the definition. The definition of limit, we have it, we understand it, hopefully, and now we can focus on the main stuff. For example, the next definition. We say that f of x is continuous at x0 if the limit as x goes to x0 if the function is exactly the value of the point. And wow.
Is it bidirectional?
It's a definition, yes. All definitions are bidirectional. Right? That's what continuous means. Example. Say the class is over and I go home. You have more classes, but let's forget about that. If I ask you, if I will ask you, where am I going? What will you answer? That's not a math question, that's an English question. What will you answer?
Home.
Home, thank you. Right? That's, do you know whether I arrived home safely or not? When you answer? Someone asks you where is it gone and you say home. At this point, do you know whether I got home safely or not? No, you don't know. That's the idea of limits. Where is the function going? It doesn't matter if it got there or not. If the function actually got to the limit, then we say it is continuous. If I get home, then my story is continuous. If I fall into a sewer, how do you write sewer?
Yes, that really.
That is, if I fall into a sewer manhole, right? On my doorstep, my movement was not continuous. Okay, so we have these two questions. That's the definition of continuity. The left hand side of the equation asks, where is the function going? Where is it aiming at? The right hand side is where it is arrived. And if the two are equal, then we say it's continuous at this point. And if they are not equal, then it's not continuous. Let's look at a couple of examples. Example, say we have f of x equals when x is different than 0, that's 1. When x equals to 0, that's 2. So now answer me, riddle me this. What is the limit as x goes to 0 of this function? What do you say? One. Because we don't care about the value of the point, right? Or an arbitrary an, which is different than 0, but it's close to 0, tends to 0. What can we say about f of an? It's always 1, right? The limit is 1. However, what is the actual value at 0? 2. The value at the point is different than the limit, therefore the function is not continuous at 0. The function wanted to get to 1, but it fell up a manhole because it's all upstairs. It was not, it didn't fell, it was abducted by aliens, okay? And the aliens were at height 2. Let's see it in GeoGebra as well. And not open, sorry. Clear all. And the function f of x equals if x is not 0, then 1 else 2. Okay, you see? So it's hard to say, but when I press on the function, you see the little dot here. That means that at 0, the value is 2. And if you're looking at that line and ask yourself, where is this function going? You will obviously say 1 because it's constant, right? It stays on 1. But then at the very moment that the function should arrive to 1, it suddenly was abducted by aliens and got to 2, and therefore this function is not continuous. Any question so far? Pi values, value was, oh, how do you write it back to? Maybe. Thanks. By aliens. S I 2 at x equals 0. Okay. Any questions so far? Let's look at another example. Is the following function continuous at x equals 0? The function is where x is larger or equal to 0 than x1. When x is smaller than 0, then it's -1. Do you think that function is continuous at x equals 0?
What do you mean? It's x equals 0, yes.
But why not?
I mean, because it switches from -1 to 1, there's some continuity there.
So is there a continuity or is there not continuity?
What does it mean continuity? You mean x0 or x equals 0?
Same thing.
For the same.
Continuity is at a point. That's the definition. So x0 is 0 in my example. I'm asking whether this function is continuous at 0.
No.
Why not?
Because the limit is not the same as x0.
What is the limit?
It's at 0 it's 1.
And what's the value at 0?
1.
So
No, not x equals 0. X0 at some point would be like, I don't know, 0 minus 2, like -1/2.
no, but 0. I'm asking about 0. So we are asking whether the limit as x goes to 0 of f of x is actually equal to the value of f at 0. That's the question. That's the question of continuity at 0. That's by definition, right? So again, I'm asking you now that you see the formula, I'm asking all of you, is that true or not?
Do you have to state if it's a 0 plus or 0 minus, or
No, like this.
then it's not because it's different?
So what can you say about the limit?
It's not continuous because
No, the limit by itself.
the limit by itself.
If the question was what is the limit, what would you answer?
Fine.
It's not, does not exist. Exactly, that's the problem here. The limit does not exist. Therefore, there is no continuity. And why does the limit not exist? So first of all, I'll show you in GeoGebra and then I will write it formally. So the function is g of x equals f if x is larger or equal to 0 than 1, other 1 minus 1. I think it's obvious this thing is not continuous, right? It has a
I believe
yes.
there's a limit there.
Yes, but there is no limit. Why is there no limit? Because in order for it to be a limit, then for every blind brother, for every way to approach the zero, the y value must be the same. But if you take an bigger than zero that tends to zero, any arbitrary sequence, then f of an is 1. And if you take Bn which is smaller than 0 but tends to 0, y value would be -1. Therefore, there is no limit. Agreed?
Yeah.
That's why it's not continuous. I don't even care about the value of the actual point. Because for continuity, it must be that the limit is equal to the value of the point. If there is no limit, there is no continuity by definition, and we're done. Yes.
Can we say that there's no limit because the limit of it to
Yes,
zero
I will
minus-
write it. Theorem onward. The limit at x equal to 0 of fx is L. If and only the limit at x goes to x0 from the right is equal to the limit as x goes to x0 from the left. And they are both equal to L. Why is it so easy? Because every sequence you can take into two partial limits, the one from the right and the one from the left. Again, I leave it as homework, but it's quite easy to from top to bottom, it's obvious. From bottom to top, like I said, take an arbitrary sequence that goes to x0 and split it into two subsequences, and f of the both of the subsequences will go to L. Therefore, the entire sequence will go to L. Okay, so yes, you can split it into right and left. Okay. Any questions so far? Okay. And next example. Take a look at the function f of x, where when x is different than 0, it's also different than 9. When x is different than 0, then it's equal to 1 over x squared minus 1 over x squared. And when x is 0, the value is 0. Is f of x continuous at 0. And again, for Samit's question at the start of the class, where do we use limits? You see that I think that's the first concept that in our head we think we understand what is continuity, but in order to actually define it, we need limits. Okay, and this will be another example of that. We'll see in a few seconds. Is that function continuous? So first of all, take a look. If x equals 0, we cannot plug it in that expression, right? Because we're not allowed to divide by 0. But it's okay, because when x equals 0, we plug it in here, and the value is actually 0. So this kind of function in Hebrew says a sim, like a sim of genes, right? Tefel. It's a function that was sewn together, stitched, whatever, stitched, maybe I think it's a better translation. So it's a stitched function. We took an expression that is undefined at 0, and we made a little patchwork there and a stitch. and we set it 0. We got a new function. And now we ask whether this function, new function, is continuous at 0. So what do we need to verify in order to know if it's continuous?
When the limits.
So what is the limit as x goes to 0 of the function? So first of all, the limit does not care about the actual point. So it's the limit of the expression above. So it's that. What is that limit?
Your
E to the power, I'll have you of minus x over 1 over, sorry. 0. What's 1 over 0 in general?
minus infinity.
It depends on the sign, right? Do you know the sign? It's plus, because the x is squared. If the x was not squared, it's a whole other function, a whole other answer. But because that x is being squared, then the 0 here is positive. So it's e to the minus of infinity. What's e to the minus of infinity?
0.
Yes, which is 0. So that's the limit. What is the actual value at 0 of this function?
0.
0. So what does that tell us?
That it's continuous.
Continuous. The function is continuous at x equals 0. Now let me show you in GeoGebra.
If the function wasn't stretched, would it still be continuous?
No, because it's undefined at 0. So it just takes the expression. It's undefined at 0, and then it's not continuous if it's undefined. So f of x is if x is 0, then 0, otherwise e to the power of minus 1 over x squared. So that's the function. And it's actually continuous. Why it shows 2 points. It thinks the value is 0, just near 0. That's a calculation mistake by the program. But you can see, and you would have guessed this function to be 0. Any question? Let's look at another example. Now, the function is sine of x over x. Is that continuous at x equals 0? Definitely no. Or definitely Haley, I would have guessed that. Definitely not, because the function is not defined at x equals 0. The limit does not even matter, like Metallica says, and not exactly what it said. But I wish to show you it on GeoGebra as well, because this is interesting, I think. Let's look at sine of x over x. Look up. ready to be wow. That's sine of x. What do you expect before I draw it? What do you expect sine of x over x to look like? Yeah, so Sammy shows me an asymptote, right? It's wrong, of course. It's not my fault. It's a bit, but okay. So that's the way the function looks. Does that look continuous to you or not?
Very much, yes.
It looks continuous, but it's not. In see, removable discontinuity. It says there is discontinuity, but you can catch it out. So I'll copy it and explain. In Israel High School, we will call such a point a hole. Why? This is a removable continuity. Okay. Since we can stitch it out. If we look at the function that for every x other than 0, it's the very same function we're looking at. But when x equals 0, we define it to be 1. That function is continuous at x equals 0. So you can't say it's the same function, right? If you have holes in your genes and you patch it, it's not the very same genes as it was. You did something, you changed something. But the idea of removable continuity is that by changing only one point of the function, you can make it continuous. Okay, any questions so far? So I will write this as a definition along with a couple of other things. Definition. One, if the limit as x goes to x0 of f of x equals to f of x0, then f is continuous at x0. That's not a new definition, that's the very definition I told you before, but I like it to be in that set of definitions together to keep the order. If the limit as x goes to x0 of f of x exists and is some finite number, exists and is finite, but the limit does not equal to the actual value at the point, or f is undefined at x0. So what do we call that? Hint just told you.
Disjoint.
Removable continuity. Removable continuity. Because the function has a direction, the limit exists, but for some reason, it's not the actual value of the point. That can be fixed. If I just change the value of the point, I will get a continuous function. It's not the original function, but it's just a change of one point, so it's not that horrible. Yes, Tom.
We said before that you can change a finite number of elements in a series.
It's not the same as function.
Yeah. But what I mean is like you're here mentioning one point, but it has to be everything but one point. you can say like there's like 5 different points that are in continuity and you can patch them all out or how is
Yeah,
it?
it's different. When I talk about continuity, I talk about each point differently. So when I'm talking about a certain point, I'm looking at the area of this point, but that specific point. If you have 5 removable discontinuities, fine. It's not something that you do. It's something that you will see in calculus 2. I think we use it sometimes. We should say the function has an area, is integrable. Then we'll say, oh, it has the removable discontinuity, and if we fix it, then it's continuous, and because it's continuous, it's integrable. And then we say change of 1 point does not change integrability, right? That's the kind of argument that we will use. For this course, you probably just need to be able to answer whether this point is continuous, removable discontinuity, or the other two I'm about to say. Yes, Sam.
Removable continuity or removable discontinuity?
And discontinuity, you're right. Every continuity is removable if you work hard enough and destroy it, you're right. Removable discontinuity. 3. If both one-sided limits, if the limit from the right exists and finite, and the limit from the left exists and finite, but
It's a field.
both it is a field, not general one. Both exist and finite, but different from one another. The limit from the right is different than the limit from the left. We saw such an example. Do you remember the example like that? This one. The limit from the left is different than the limit from the right. Then it's called a Hopf discontinuity, or it's not the professional term. Then x0 is a first order discontinuity. Hopping discontinuity. In Hebrew, I say irretziput kpitzatit, pizza, because the function hops from one value to the other. But it's considered a first order. And it's funny that it's a first order because we had a discontinuity before, but the other one is considered by mathematicians to be almost continuity. So that's actually a discontinuity, right? It's not, you cannot fix it. Actual 2 different y values.
Just put the stick in the.
Yeah. Okay, and lastly, any other case is a second order discontinuity, meaning one of the one-sided limits does not exist or is not finite. I'll give you one example. Let's take a look at e to the power of 1 minus 1 over x. So it looks a bit similar to the example from before, only the x is not squared here, and it actually matters. You see why? What is the limit as x goes to 0 of e to the power of 1 minus 1 over x? So it's e to the power of minus 1 over 0. But now we are not sure what it is because it could be positive and it could be negative. We must split into the two sides. If we take a look at the limit from the right, what will we get?
From the right. Minus infinity.
Yes. So that's e to the minus infinity, which is
So. 0.
0. But if we look from the left, 0 minus. But if we look from the left, we get e to the power of minus 1 over negative infinity, which is e to infinity, which is infinity. Therefore, x equals 0 is a second order discontinuity. And I don't care that on one side it was finite and nice, and it's not a so-called hopping discontinuity, because for hopping we need both sides to exist and be finite. Once you have an infinite something, then it's a second order discontinuity, it's completely unfixable. By the way, from a calculus 2 point of view, it does not have an area, it's not integrable, it's really horrible. Not every second order is not integrable, but if it's not finite, it's not integrable. Just second, Sunny, I'll just draw you this example, and then I'll listen to your question. E to the power of 1 minus 1 over x. Look at how it looks. You see, from the right, the limit is 0. From the left, the limit is infinity. And again, notice that we started actually learning calculus, if we can say that, right? Because we have the ideas of limit, the idea of limit, hopefully you understand something about it. And now we can actually talk about functions and their properties using limits. Yes, Adam.
So, how does this affect the way that we're calculating limits? If we had.
No, it does not affect how you calculate limit. It's the other way around. You calculate limit to classify the function. You want to study about the function to know whether there is an area under the curve. And for that, because of calculus 2, it's just one example, but it's the main example in first semester, first year. In order to know if the function is integrable, it has an area under the curve, you need to know it's continuous and bounded, and the limits help us know that.
Here we're calculating limits from different directions, which
Yes.
is completely different to how we've been calculating the limits of.
Sequences. Yeah, because functions are a bit more complex than sequences. Sequences, that's when we start with sequences. You have only one direction, it's easy. And now with
Okay, so
function,
I'm getting confused because when we've been talking about series, we've been also graphically representing that, which is why I'm different.
no, but again, series are also sequences. You just sum up in the same direction. Functions are much more complex because there is a limit at each point of the x-axis, right? At each point there is an infinity and you can talk about a limit. And also you can go from the right and the left, you can go through the real numbers, not real, the rational numbers or irrational numbers, right? There is much more complexity with functions rather than with sequences. You just go first element, second element, third element, and series and sequences are the same in that sense. But that's why we did most of the hard work with sequences, and now I can easily tell you it's 1/-0, it's minus infinity. See, we have the ideas of limits and we can go faster studying this and this is actually what we need, right? Afterward there will be differentiability and what. Any other question? So that's enough for today, and I see you on Tuesday. This week there is Tuesday, right? Next week's Cowboy.
Did you trade yet?
You were right, there is no class.